Hello fellow problem solvers, so today we're going to be doing a problem from the Serbian team selection test from 2014, problem number 1. I suggest you try this problem out for a minimum of 20 minutes, ideally an hour to 2 hours, not more than 3 hours. If you'd like to go along with us, give this functional equation a go for the next 15 minutes. And now without further ado, let's begin. So, we have function from the final functions from the reals to reals that satisfy this relationship. Okay, it's an interesting relationship right here. Let's see what happens. So, what is maybe the first thing you notice in this function? Now, for me, the first thing I notice is that this side is completely symmetrical with respect to x and y. Like if I exchange y and x, nothing happens. Versus this side, not so much. In fact, I get, if I exchange this place of y and x, I'll get f of y f of x minus x f of y is equal to f of xy minus xy, right? Which is, I get these two things are equal. So that's like the first sort of the immediate first thing I noticed. The next thing is like, well, let me set one of them to be equal to 0. What does that give me? It gives me that f of x f of 0 is equal to f of 0. Pause for 2 minutes, ask yourself, what does this mean? And the answer is, well, this either means that f of 0 is equal to 0 or f of x is a constant. How can I see that f of x is a constant? Well, if f of 0 wasn't 0, by plugging in x equals z over f of 0, I'd get f of z is f of 0, and ergo, I'd finish the problem. But a function is obviously not a constant, otherwise it implies both x and y are equal to 0, which is not true for every single x and y. So, because this is not the case, then we know f of 0 needs to be equal to 0. That's pretty cool. So if f of 0 is equal to 0, let's see what happens when we plug in, say, y is equal to 1. Just see if we can take advantage of this sort of thing we've noticed here. Actually, let's just say, pause for a second and see, like, what is this? If this is the same as this, like, can we figure anything out immediately from the outset, or do we have to plug stuff in? So you have, say, f of 1 is equal to a constant c. So then we have xc minus f of x is equal to f of x minus x. Oh, it's not really super duper cool. Also, what's the solution to this? Is it some linear combination x and y? Right? Like, what is it c minus xy, then this is c minus 2xy. This is then c. The c's cancel out, we get minus xy. Minus x, so it's not, doesn't seem like it's that. Like, that's also a good question. Like, what is, maybe it's f of x is x? Yeah, f of x is x does seem to work out well. So maybe that's a solution. Now, here I'm thinking, which numbers does this cover, right? For y and x that are different, right? For which numbers do we have f of z is equal to f of negative z? Right. When is it the case that we have this? That's what I'm thinking about. And what this is prompting me to think about is this an injection? And I invite you here to pause for 10 minutes and figure out what your next steps are. I think this is a good sort of interesting pausing point. And now let's continue. So let's see what happens if f of a is equal to f of b. Then it makes sense. Let's put in y is equal to a, and I'll get f of x, let's call this thing d, xd minus a f of x is equal to f of ax minus ax. I'm thinking, is there some x that can give me, I don't know, that can just like give me something cooler than this, right? Bx minus bx. does it have to be an injection is my thinking. Also, we haven't plugged in x equals y, which is sort of strange by now. If we plug in x equals y, what do we get? We get this thing right here turns into f of 0, and we get f of x squared is equal to x squared. Okay, so this is it's a bit funny like that I did not plug this in to begin with. But you know, like you try different things. Like this is what functions are about. You have a bunch of different ideas that you want to try out. Though plugging in these two to be equal, like sort of wasn't maybe an immediate miss that I maybe should not have had. But anyways, let's continue. So what does this imply? Well, this implies that f of a is equal to a for all a which are in the positive real numbers, right? Because we can set x to be square root of a if and only if like a is a positive real numbers. So now we have that the numbers that are greater than 0 are covered, and our trouble is with the numbers that are not greater than 0. Okay, what are we going to do with the numbers that are not greater than 0? Pause now for 5-10 minutes. And one idea is, well, this thing we had here, you know, this is of the form f of z is f of negative z. Wait, but then is the absolute value of z a solution? I don't know. It's a cool question to ask. So let's actually plug in some maybe. What happens if we plug in x and y that are both greater than 0? This is greater than 0. We have f of xy. Oh, we get f of x, so we get xy minus xy, we get 0 here. And here we get 0. Okay, so we don't get anything if we plug both x and y that are greater than 0. But not to worry, let's plug in both x and y, which are then less than 0, question mark, or plug in one of them that's equal to 0. So if we plug both of them that are less than 0, actually let's plug one that's greater than 0, just for the kicks. Let's set a y to be greater than 0. So what do we have? We have this is going to be then f of actually which one are we're going to use this one. F of so y times x minus f of x is equal to f of xy minus xy. Now let's set x is less than 0, otherwise it doesn't make much sense to look at this. So is there anything interesting going on here? And also f of y times f of x minus x is also equal to the same thing. Okay, so do you find anything here that's interesting? For me, personally, it's like I'm getting z and negative z. So one of these is positive, right? So now if x is greater than f of x, then I know this is positive. Like say we take them into these two cases. Then what do we have? We would have f of xy minus xy would be equal to y times x minus f of x. Interesting. For like a negative x, for x less than 0. And then what does this mean for us? Like the sort of worry here is that how much is this really giving us? Though wait a second, when f of z and f of negative z are equal, they're equal to the absolute value of z in this case, right? Now, this z will always be 0, we know that. If f of x equals to x is our only solution, but when this is the case, they're both equal to the absolute value of z. But it still doesn't tell us for all the negatives where they go. Now, maybe, what am I going to do with you, baby? So, this does not... Do you see anything from here? I, frankly, do not. I just don't see anything. X equals 1, maybe? Ish? No, wait, I can't say x equals... I can set y to equal 1. And if I set y is equal to 1, I'll get f of x minus x is equal to x minus f of x which implies x minus f of x is equal to f of x, which is a contradiction. Here, if x is less than f of x, then I'd get that they're equal, that f of this, that this in fact, that have f of xy minus xy is equal to y times f of x minus x. Now if I plug in y equals 1, I don't get anything. So for negatives, I have this to be the case. F of x is greater than or equal to x. So why am I still not done with the problem? What are we missing here? What are we missing? That is the question now. If I just plug in here y is equal to 1. If I plug in y is equal to 1, I'll get f of x minus x is f of x minus f of x. Now if f of x is greater than or equal to x, then this thing right here is negative, but it's equal to f of x minus x. So what is f of x minus x equal to? I don't know that yet. What happens if we plug two numbers which are less than 0, then this side will be 0, right? Maybe we can prove that there's only one number such that f of x is equal to 0, right? So let's maybe say f of alpha is 0, and let's see what happens when we plug in, say, y is equal to, let's plug in x is equal to alpha first, because I just want to get rid of this thing. So then I'll get f of alpha f of y is equal to minus alpha y. Wait a second, my dear boy. What does this mean? Well, this means that if y is greater than 0, then I have f of alpha y is equal to negative alpha y. I mean, alpha then has to be less than 0. If, say, alpha isn't equal to 0. But that gives me f of the negatives. F of x is equal to negative x for all x which are less than, what's it called, 0. Because I just set y to be equal to, if I want a. So y is going to be equal, so I'll just say positive number if alpha is less than 0, and it has to be by everything we found so far. Then I'll just set y to be equal to z over alpha. And actually, I'll set it to be negative z squared over alpha. This way, this is a positive number. And then I'll get f of negative z squared is equal to negative z squared, which is going to be z squared. So then I'll have f of x is the absolute value of x if there exists f of alpha equal to 0 for some alpha less than 0. And then if we check the solution, like if x and y are both, if x and y are both negative, yeah, but then this doesn't actually work out, does it? Because this doesn't work out because then alpha doesn't work. Or actually I could just set here, I could set alpha y is equal to alpha 2, and then I'd have f of 0, which is 0, is equal to minus alpha squared, so alpha is equal to 0. So they can only be, okay, so there can only be one element which goes to 0, and that is 0. So now if we set, like put x and y, which are both less than 0, what does that give us? It gives us a 0 here, but it gives us f of something is equal to 0. And so it means that a thing inside f, which is x f of y minus y f of x, is also equal to 0. Now what does this mean for x and y for all x and y less than 1? Well, I invite you here to pause for 3 minutes and try to figure this out. And the answer is from here, from x f of y minus y f of x is 0, transport it to the other side, divide by xy, and you will get that f of y divided by y is equal to f of x over x for all x and y which are less than 0. So what does this mean? Well, then this is a constant. Plug, and this constant is equal to a minus f of negative 1, right? So we have that for negatives, we have f of x is equal to cx for all x which are less than 0. And now we need to actually check that these are the valid solutions. If x and y are both greater than 0, then yeah, that's no biggie. Let's check the solution. If x and y are both less than 0, we get that this thing right here is going to be cy, cx, cyx. That's 0. We're good. Now, what if one is less than, one is greater than? What does that give us? Well, that gives us, say x is less than 0, y is greater than 0. Then this thing right here is going to be f of x times, so y is greater than, so it's x times y, minus xyc. And then this is going to be equal to xyc minus xy. So this is going to be equal to xy c minus 1. And then this is also equal to f of xy c minus 1. We've been told nothing about this constant just yet. But now we can see that if this constant is, what is this going to equal? So this is x times y c minus 1. So if c is 1, then we have one solution. So if this was positive, let's actually look at this, because this is actually pretty cool. When is this positive? xy times c minus 1. Well, because x and y are negative, this is positive if and only if c is less than 1. And if c is less than 1, then the f of this is equal to f of this, and we are done in this case. That gives us a solution. If c was greater than 1, then we would have, so if c was greater than 1, then this would be c times this. Then we could cancel them all out, and we'd get that c is equal to 1. Contradiction. So c is either 1 or it's less than 1. Now if I do y is less than 0 is greater than x, I'll get x times y times. Actually, wait a second. This is supposed to be 1 minus c, not 1 plus c. Let's double check our arguments now. And this is meant to be xyc minus 1. So now, the opposite argument actually holds true. Let me clear up the board here. So we have this thing right here is true. And now we can go by case scenario. So if c is equal to 1, then we have the solution we already had. Then solution. So if c is greater than 1, this is less than 0, this is less than 0. And if c is greater than 1, then this thing right here is, actually let's look at this thing first. If c is greater than 1, then this is negative, times a negative is a positive. And then we'd get xy, 1 minus c, is equal to xy, c minus 1. Then boom, cancel, and you get a contradiction. You get minus 1 is equal to 1, a contradiction, because this is negative of this. So that can't be right. And if c is less than 1, then this thing right here is equal to what? If c is less than 1, I like to write it 1 minus c is greater than 0. Then this is negative. And then we'd have, this is c times xyy minus c times sum a is equal to negative a, boom, boom, then c is equal to negative 1. And here what we would have is, if c is less than 1, we'd have, like this is the other case we need to look at, then c minus 1 is less than 0, and then this is equal to this. Wow! So a solution is f of x is equal to x, and a solution f of x is the absolute value of x for all real numbers x. Those are the two solutions. We've sort of checked them out, and in checking out that this is a solution, we found the other one. And this finishes up this beautiful functional equation. I think it's a very nice problem because it illustrates, you try something, you're going this, and then wait a second. I have all the positives are equal to 0. And then boom, bada-bam, do I have any other zeros? No, I have only 1 0. That's a common sort of thing. Like if you can't prove an injection, try to prove that you have a specific number that's always a 0, because zeros can just like, boom, 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 cancel stuff out, as they did here. And then from there on, we notice, oh wait, the absolute value of x is also a solution. So this finishes up our problem, and as always, thanks for problem solving.